So, the question that we're going to be addressing today is how does glucose enter glycolysis, as well as other types of carbohydrate. Okay. Pardon? Yes. So, what you have to think about is most of your food is not going to be just glucose, right? And so the way that you're breaking down, even if you're eating things that are sugar, carbohydrate rich, then it's not going to be just glucose. So there has to be ways that it breaks it down and enters it into glycolysis so you can get the energetic components out of it. So I was trying to be cute there. But let's to the hips, the fate of carbs. So now what we're going to have to do is look at each of these different types of carbohydrates and think about how they can be transformed either into something that's called glycogenic, some type of either glucose derivative or intermediate of glycolysis. So glycogen and starch are the storage polysaccharides. And I've always used these terms exogenous and endogenous before. Endogenous is what your body makes itself. Exogenous would come from your diet from outside. And one thing that we are not going to do is look at really large polysaccharides. We're going to focus on things such as the disaccharides on down. Okay. All right. This is the big picture. This is the sheet that I put on my fire. That way you just fill it in as you go along. That's essentially what this is. And then one of the other sheets I think is for lactose. This galactose is a little special. Well, we're all special in God's eyes. Okay. So first up, we're going to start with lactose. So if you're following around, there's lactose. Lactose is a disaccharide. Okay. In case you didn't know, it's made up of glucose and galactose. So the first enzyme that we would have to break down lactose, does anyone know what it's called? It's this one right here. What's the very first enzyme that's going to come down and break apart lactose? I thought someone said it. Say what's in conviction.
Lactase.
It's lactase. So from lactase, you get two products. All it does is hydrolyze the disaccharide. And so you're going to get glucose and galactose. So next up, we're going to look at the fates of glycogen and starch. We'll hit up the galactose and glucose itself in just a moment. But we see glycogen and starch. So there are two possibilities here. Because what is glycogen made up of? It's a polysaccharide. What's it made up of? No, what sugars is it made up of? Sorry. What sugars is glycogen? And starch for that matter.
So 2 glucoses.
Well, it's not just two, but it's multiple glucose, right? It's just glucose, right?
Okay.
It's just stored glucoses. Mm-hmm. It's going to be at least 2. All right, so when it breaks apart, there are two possibilities here. One product is going to be D-glucose, so it's covered by this enzyme. Another possibility is to make glucose 1-phosphate. Okay, it doesn't matter to me which way we start off with. Do we want to start going on the one that's vertical or the one that's horizontal? Horizontal or vertical? Because find out some people don't think that way. It doesn't matter to me. Which one do you want to cover first?
Yeah.
Vertical. Okay, so we notice there's water that comes. Water is used as a nucleophile, and we break it apart, and we get glucose. All right. So what enzyme does that? What is that enzyme? This one right here. Think about something with starch, like a bread or whatever. Pop it in.
Amylase.
It's amylase. Okay. In particular, which one? Which isoform? It's alpha amylase. I can't hit next because it shows up both of them. So that's the easy. Well, I don't know. That is what it is. Okay. Glycogen and starch. What class of enzymes can do this? Let's think about your enzyme classes, which we could always review your enzyme classes. You've got, we won't do it right now because of the fact that I've already got the recording started. That can take another 10 minutes. Notice, glycogen. We have, what's the PI stand for? Inorganic phosphate is being added across to form glucose 1-phosphate. So there's a possibility someone says phosphatase and phosphorylase. Okay, what do phosphatases do?
Transports phosphate without ATP.
Right. So it's the one that's going to transfer the phosphate without the use of ATP. What do phosphorylases do? So phosphorylases are the ones that transport phosphates without ATP. So what does a phosphatase do? It breaks it apart. And usually give off PI. That is correct. Okay, just wanted you guys to think this through. All right, so we have a phosphorylase, we have a phosphatase. Depending upon which direction you go, you can possibly see that. Which of those two does it make the most sense here? We have glycogen, which would be at least 2. For example, glycogen would be at least 2 glucoses, and it gets this enzyme. We're going to be breaking it apart and adding an inorganic phosphate to it to make glucose 1-phosphate.
Phosphorylase.
It's a phosphorylase. Okay. If you're going to be specific, this one's glycogen phosphorylase. If it's for glycogen, starch is a little bit more. So they just put it on this slide. They just put the generic phosphorylase that we find at this point. When we start talking about glycogen itself, it would be glycogen phosphorylase. Okay. All right, so this is just to show you a little bit. This one's not included on that one sheet, but just to give you the breakdown. This is glycogen phosphorylase. It does not require ATP. This came from the old book, but I like it in the sense that it kind of simplifies it down. We can see glucose there. What does that N mean when it says parentheses N?
A lot of glucoses.
There's a lot. N could equal 1,000. Just it just comes from math. Takes an inorganic phosphate. We now have glucose N minus 1, so there's 1 less, and we've got a glucose 1-phosphate. So that's why it should make sense now that this is a phosphorylase. It's transferring the phosphate without using ATP or any of the NTPs technically. Also, there's a potential problem. Okay, so I don't have this one covered. Oh, what a shame. With glycogen, and I think we even discuss it later on, maybe next chapter in greater detail. But glycogen it doesn't just look like this. Whoa, sorry about that. That'll make you sick. It doesn't just look like glucose, a bunch of little glucoses in a row. Remember, there are some that will branch off like that. Glycogen phosphorylase cannot work on the branches. Okay. And so, it can work on cutting it down this way, but it can't work on this portion right there. What does that's called the debranching enzyme. It's one of my favorite named enzymes. So I would know how to do. And what do you suppose? What enzyme adds the branches?
Branching.
It's the branching. Yeah. And so that's why the name tells you exactly what they do. It is a common name. There is a big BC official name that's up in enzyme stuff in it. But what happens is once it gets down to about 4, the phosphorylase can't fit anymore for it to work. And so then the debranching enzyme comes, and what it does is it takes 3 of those 4 off and sticks it on the next available branch, next available end. And that way the phosphorylase can just come right along. Okay, and this one can also be hydrolyzed as well. Okay, once you get down to just the one. Okay. Now, on that sheet, I've just blown this up from the other book. But on that sheet, we had glucose 1-phosphate. That was what phosphorylase made. But it's not in glycolysis. Remember, whenever I didn't write it out, but you may want to just rewrite out just the thing. We start with glucose, and you had hexokinase came, and hexokinase went from glucose to what was the product of hexokinase?
Fructose.
Not fructose 6-phosphate. Glucose 6-phosphate. It took glucose and it made glucose 6-phosphate. Okay, for hexokinase. So we have to transform glucose 1-phosphate into glucose 6-phosphate. Right? This is an isomerization reaction. So what's one of the classes of enzymes that can do an isomerization reaction? It's a mutase. This one is a mutase. So please note it is reversible. So what would be a good name for this one? Not only just glucose mutase. What's
Hexose.
Oh, I could even see where it, but no, I was going for the phospho part. This is phosphoglucomutase. Okay, but yes. It should make sense, right? It's literally isomerizing different isomers of glucose phosphate. So that's here. I'm going to go back to this one. It's on there. It was just blown up. So now we can see we went from glycogen. One thing is we could have made glucose directly using alpha amylase, but you can use the glycogen phosphorylase to make glucose 1-phosphate, which has to be mutated in order to make glucose 6-phosphate. Which glucose 6-phosphate is that an intermediate for glycolysis? Don't overthink this. Is that yes? And so what enzyme goes from glucose 6-phosphate to fructose 6-phosphate? PFK would be, what's the K in that?
Is this one phosphoglucose isomerase?
Right, this is an isomerase reaction. And so that's why it's because where is PFK on here? It's not written, but what did PFK do? If the K is a kinase,
Oh, it's 6-phosphate and 1,6.
right, it's fructose 6-phosphate to fructose 1,6-phosphate. So that's why if you have that sheet, you can even write that on there, even though there's not a box there. It's just to help you hone in on thinking about glycolysis. All right, now we're going to look at trehalose, which is up in the upper left-hand corner. Trehalose. Okay. What enzyme do you suppose breaks trehalose down into glucoses? Trehalose, by the way, has multiple glucoses as well. I can see where you could. Okay. It is not amylase, okay, but you can see it does a very similar reaction. What did lactose? What enzyme does lactose?
Lactase, true.
So if lactase does lactose, blank does trehalose. It's sort of like a little SAT kind of question, right? It's trehalase. One that's kind of hard for me to say. But yes, it's specific. It breaks down trehalose into glucose. All right. So now if you look at sucrose, that's one that you may remember from biology. It's a glucose and a fructose connected together. What enzyme breaks it apart to glucose and fructose? This is an enzyme that you probably talk about in biology. I don't know that you talk about trehalase, but lactase, amylase, and this one you probably do, either in biology or AP or something. Those are both pretty common carbohydrates. It's sucrase. Don't overthink it. Lactase is lactose. Trehalase is trehalose. Sucrase is sucrose.
That's what I was just.
What?
So crazy. It was funny when you were thinking about it.
Yeah. You're so crazy. It just sounds like it's gonna be. That almost started to sound like it's gonna be a borderline ethnic slur there. So. Sucrase. All right. Oh boy. And now someone just gets it. No. That's okay. So, next up, what happens to the glucose? Nathaniel.
Yes.
D-glucose uses an ATP to make glucose 6-phosphate. What class or classes of enzymes can do this? It's a kinase. So what is this kinase? It's hexokinase. I know I had some people that got confused because it wasn't the nice straight line that you usually see because it's curved. But yeah. All right. Next up, we have to think about the different tissues, and so we're going to look at the fructose. And fructose, it matters because there are two different pathways. The one pathway has to do with the muscles and kidneys, fructose and muscles and kidneys. And the other pathway, the one that's on the lower end, is the one that has to do with the liver. Okay, so if we look at, what's it, the diagonal one? Fructose, D-fructose, uses up an ATP to become fructose 6-phosphate and enter into the glycolysis. What class of enzymes can do that? What class of enzymes is going to go from fructose, uses an ATP to make fructose 6-phosphate? That class of enzymes would be kinase. So what kinase could this one be? Phosphofructokinase? Oh, possibly. What's another possible name? What one? There's possibly fructokinase. I thought someone said hexofructokinase. That's really interesting. This one, it's just hexokinase. If you think back, I kind of even pointed this out. Remember, hexokinase, it's more promiscuous. That's the word that we use in enzymology and biochemistry, in that it accepts more than one substrate. And it literally means 6 carbon-containing sugars, and then it'll phosphorylate it. And so that's why when you say hexofructokinase, it's like, oh, so close, so close, so close. All right. Now let's think about fructose in the liver. We have D-fructose, uses an ATP to make fructose 1-phosphate.
Hexokinase.
Okay, so you say, oh, it's hexokinase, right? That is a great guess. Okay, now little I don't know story, little tale to tale. So the liver, what is the function of the liver? Okay, it kind of filters. Is what?
Stores sugar.
It can store sugar, it filters. What else does it do?
You donate it if
You can what?
you can donate. You can donate your liver, and then part of it.
Yeah.
Could be a function.
So your grandmother asked you, why does someone eat their liver? What would you say? You store sugar. I store sugar in the candy canister or whatever. That kind of thing. Well, how would you respond? Filter. Well, what about the kidney? What does the kidney do? Well, if that's true, if it's only filter, then why doesn't it do the same thing the kidney does? How many functions does the liver do? So some way I read, and I don't know how they did this, they came up and they said it's like just over 500 different functions in the liver. The liver does a lot, and if you haven't noticed so far, we've talked many times about like the liver isozyme or the liver form of an enzyme versus the other forms. Same thing with like the heart. You know, the heart. You can imagine why does it make sense that sometimes the heart has different isoforms for enzymes? What can most other organs and muscles and stuff do that the heart can never do? Rest. Okay, right. You can't stop it. Well, you shouldn't stop. Don't stop your heart, please. But yeah, well, the liver is the same thing. Well, it's not that it can't rest, but the liver does so many different functions that, and the rest of your body depends upon the liver in many ways that it oftentimes have different isoforms. This is also true. This is not hexokinase. This one's called fructokinase, and it's specifically for the liver isoform for it. Another big difference, what's another big difference between hexokinase and fructokinase? They both can use fructose.
The location of the phosphate.
It's where they add that phosphate on, okay? Hexokinase will do it in position number 6. Fructokinase will do it in position number 1. Which you may say, but look, if you look at the fructose, how do you know which one's 1 and which one's 6? Once again, it's based off of the original glucose numbering. But they aren't exactly identical because positions, let's see, 3 and 4 have their alcohols on different sides. Okay, so it does matter. And another reason why, in general, like in kind of Miss America World Peace answer, that the liver many times has different isoforms is because by having this compartmentalization at the organismal, what's the word I'm looking for? The organ level? I can't think there's the word there that's from like anatomy. It's in my mind. But at the level of the organ allows you for the liver not to compete at different times. And we're going to see the same thing later on with respect to hexokinase. The liver has to have hexokinase as well. It just uses hexokinase for glucose, not for fructose. All right, so we have fructose 1-phosphate and fructokinase. So let's continue on with that. If you look at, we have fructose 1-phosphate in the liver. We now have an enzyme that breaks it down to glyceraldehyde and dihydroxyacetone phosphate, which we more commonly and lovingly refer to as Sorry, channeling my inner Justin Timber. Sorry, that's so lame. All right, so but we have glyceraldehyde and DHAP. All right, if this was fructose 6-phosphate in plain Jane glycolysis, not to belittle anyone in plain Jane, but plain Jane glycolysis, and we're going from all the way down here to glyceraldehyde 3-phosphate in DHAP, right? But this one's not glyceraldehyde 3-phosphate. This is just glyceraldehyde in DHAP. So you can already see where there's a possible issue right here, okay? If we are in plain Jane glycolysis, we had fructose 1,6-bisphosphate, and we made glyceraldehyde 3-phosphate in DHAP. It's not shown right there. What enzyme was that? Aldolase. Yes, that was aldolase, right? So, likewise, we have fructose 1-phosphate making DHAP and glyceraldehyde. So, what do you suppose the name of this enzyme could possibly be, or what class of enzymes? What class of enzymes could this one be? See about the logic here. What enzyme is this one? Aldolase. So, what class of enzymes is this one? It's an aldolase. Now we need to name that specific aldolase. Pardon?
The fructose 1-phosphate aldolase.
Yeah. So it's very specific. So, going along that principle and that idea there, what's going to happen to DHAP in the liver? If we're not in the liver, if we're in plain Jane glycolysis of an epithelial cell, what happens to DHAP? It gets converted to glyceraldehyde 3-phosphate, right? And what enzyme does that? What class of enzymes is it? It's an isomerase, and what one in particular? Right, triose phosphate isomerase. So would you see that that is very specific, or is it a little bit more promiscuous? Okay, so now if we're back here in the liver, and we have DHAP, and we're going to glyceraldehyde 3-phosphate, what enzyme do you suppose this one is? Don't overthink it. What? It's the exact same one. It's triose phosphate isomerase. So we've seen that, and that's nothing new. Now, what about glyceraldehyde? What is the problem that we have here? What form of glyceraldehyde do you have to have for glycolysis, normal plain Jane glycolysis to occur? D, but in particular what kind? Not just D, but it has to be phosphorylated. It has to be phosphorylated at what position? 3. Okay, what's the problem that we have here? The lack of phosphate. So, what class of enzymes can use an ATP and add a phosphate in the 3 position to glyceraldehyde? Pardon? Kinase, okay. So what could be a possible name for this kinase? That is true. If it was really specific, but it's not that specific, so it's triose. But I was going to, if you had told me glyceraldehyde kinase, I'd give it to you because that's specifically that you know. But this one, that just should let you know that it doesn't necessarily have to be glyceraldehyde. But
so what is a trio specifying? That it's on the 3rd?
what?
That's on the 3rd.
No, what is triose? Do you remember this from last semester? What does yes, I was going to say. Ose just means it's a sugar, and tri lets you know that there are 3 carbons in there. And so that's why glyceraldehyde is a form of it. There's dihydroxyacid would be. But yeah. Alrighty. So now we're gonna really switch sides there and look at mannose. Mannose, we have to add a phosphate to it at the expense of an ATP. So what class of enzymes could this be? It's a kinase. What kinase is this? It is hexokinase. Mannose has 6 carbons. It's our good friend hexokinase. Hexokinase gets around. Okay, that helps you remember hexokinase. So be it. Some slight sophomore human humor there. But we're not quite to glycolysis directly yet. We have mannose 6-phosphate. And so with the mannose 6-phosphate, we're going to try to transform it to fructose 6-phosphate. What class or classes of enzymes could this be? It is an isomerase. So what could you name this one? What's one of the possible names? A mannose isomerase? Mm-hmm. And to be even more specific? This one's just phosphomannose isomerase. Yes. If you had told me mannose 6-phosphate isomerase, I would give it to you. Yeah. Okay. All right. Are there any questions so far? Like I said, that's that one sheet that we just filled that in on there. Any questions? Yeah.
Between the deep fructose and then going to the 2 different, the 1-phosphate and the 6-phosphate.
I gotta look.
Sorry. Yeah, that right there to the 2 possible. Why is the name? What is like the logic behind the naming of the enzymes? Because it, like, why is it?
So hexokinase is more promiscuous. It's the isoforms that you're talking about everywhere else with mannose and with glucose and everything like that. Okay, so that's why it's just generic promiscuous enzyme that does all hexoses. Fructokinase is a very specific one that's in your liver. And it only does fructose and it adds it to the fructose 1 position and not to the 6th position of any hexose.
Okay, so when it says fructokinase, it's only going to be the 1 carbon.
Yes.
Okay.
Yes.
Is
I don't think that it, biologically, I don't think it does it at the 6th position relevant.
It is for hexokinase, it's always going to be the 6th
6th position.
Okay.
Same thing. That's not to say that it can't make mistakes,
Okay.
but the one that is biologically relevant would be the 6th position. Okay. Alrighty. We're almost finished, but now we're going to start to look at, if you looked up here, you know, we're going to blow this up. Okay, blow this up to see like what really happens, because it didn't all fit right there, and so your book actually separates it into, and that's what the second file is that I had uploaded. So we're going to blow this up to look at it more in depth. But if you notice, if you go to Galactose, which you can either have it as a monomer or you get it from lactose itself, it actually utilizes something that we haven't, I don't think you've seen this before. What does it do that's very, very different? What is different about galactose and its pathway than anything else that we've done so far?
Does it require an enzyme?
No, it does. But that, yeah, if you just looked at that, then you say, hey, does it require an enzyme? What else? What does it use?
UDP.
It uses UDP. And what is UDP?
Uracil diphosphate.
Okay, yeah, this is where they talk about uridylation. I have so much problems. Adenylation is really easy to say. For you, they call it uridylation. I will probably just call it udepilation. Okay, but yes, they add the U to it. Whew, it's difficult. So this is that little section blown up. All right. So we have galactose. The first enzyme takes this galactose and it uses an ATP and magnesium. All of the kinases so far that we've been talking about require magnesium. Utilizes magnesium, ATP, and it adds it at the 1 position. So first of all, what class of enzymes can this be? It's a kinase. Now think about what kinase can this be? Especially given our previous discussion, Quentin, or maybe what kinase can this not be?
It cannot be hexo.
It is not hexokinase because it's not in the 6th position. But yeah, that's the question for you. So if you're going to name this kinase, since this seems to be a relatively special enzyme kinase, since it's adding it to the number 1 position, what could you name this one? This is galactokinase. Okay, just like we had fructokinase, we had hexokinase. This is galactokinase. There's a little historical or a little side note for, you'll probably forget about it between now and then, because I think it's technically next chapter. But there is one called glucokinase, and glucokinase is hexokinase 4. Okay. It's a very, very specific one. It's for the liver and the pancreas. And the pancreas is kind of like the liver. Okay, this next portion that we're going to see is a cyclical. It's kind of drawn a little weird. The whole purpose is you're going to ultimately make this UDP glucose, and the UDP glucose does something really, I think it's cool, but a little different than what we've seen so far. This UDP glucose, which is the product of the first time that galactose is put in, is used in the reaction for the next galactose. Okay, so it's a little cyclical part that will always kick off one product ultimately from the galactose by the product from before. Okay, or by a product or a metabolite, intermediate from before. And so that's why it looks a little weird. And we haven't seen something like this so far. Okay. And I'll point out a couple things as we go along. All right, so first up, we've got galactose 1-phosphate. We have this enzyme now, And it's going to add a UDP. Why do you suppose you add UDP to things? Why do we add phosphates to things? What did I say that they are? I said it in the last chapter, I think. But why do you add phosphates? Same reason why you would add like acyl groups or acetyl groups. No, it's not really a stabilizer.
They activate something.
It does. They activate their great leaving groups. Okay, as you can see, the UDP is a great leaving group, and so it helps. Activate in that sense. Okay. So the galactose 1-phosphate reacts with UDP glucose, and it's going to kick off glucose 1-phosphate, and the galactose now is stuck onto the UDP. Vice versa, however you want to think of it. Right? So think this through a little bit. What class or classes of enzymes can this be? What's a possible class of enzymes here? There's a lot going on, but there's one thing in particular. Is this a kinase? Yes or no? No, because there's no phosphate really moving in that sense, leaving. Is this an oxidoreductase? Yes or no? No. Okay, so therefore it can't be a dehydrogenase. Okay, so then what are some other possibilities that are left? Cyclase doesn't really make sense. It's cyclic before, it's cyclic after, it doesn't really, so. Is it really an isomerase? Not in this instance, because we actually have things moving around and we have two different products. And it's a transferase. And what are we transferring? UDP. Okay, so this one's got a very specific name. It is a mouthful, but it tells you, I wanted to show this, because it tells you exactly what it's doing. UDP glucose, colon, because this is the enzyme commission kind of name. UDP glucose, galactose 1-phosphate, uridylate transferase. I think I was that one. So what that literally means, if you break down the name, the U is being transferred between UDP glucose and galactose 1-phosphate. But it's a transferase. So if I were you, I'd also find like some way to abbreviate this, because I definitely want to get to this last two. Oh, because this is very, very important. We have UDP galactose, and in this step here, it takes an NAD, and we get an NADH. Why do you think that's really important? What's so special about this NADH? What is it used for? Pardon? Ultimately, why make NADHs? Because it does what? Someone said. It's going to make ATPs later on. In fact, once again, depending on its location, it can go on to make up to 2.5 ATPs each. Notice in the second step, we also do the exact same thing. So we get up to 5 more ATPs by doing galactose than we did with glucose. So in that sense, you can think glucose is not even as good as galactose at doing this. Okay. So does anyone, there's a word that I'm sure you've forgotten from organic chemistry. These are isomers of each other, right? But with sugars, they use a special term for sugar isomers. Does anyone know what they call them? No, they are enantiomers, but it's specific for sugars. I don't even think that they use it for anything else. I can think off the top of my head. It means the same thing. Essentially, they're called epimers. 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 And so like lactose and glucose and stuff, those are technically epimers of each other. They're called epimers, so if you notice the only difference is the alcohols flip on position 4 from being an alpha to a beta. No, from being beta to an alpha. That's the only difference. This enzyme is the same enzyme. It does 2 steps. Kind of give it away. Normally don't give it away. So we first take the galactose and we make it into this ketone, and then we just literally go ahead and we make the alcohol that's on the other side. Okay. But yeah, it's the exact same enzyme. This enzyme is called an epimerase. I usually have people guess and say, what could it be, blah, blah, blah. We will only see epimerases a couple times all semester long. Technically, it's a class of enzymes. They are a type of isomerase. Okay. But they're a very specific type where they just literally, sort of be like a subclass, they literally will take and switch the alcohol from one epimer to the other epimer. And if you notice, it doesn't even change the carbon that the alcohol is on. So that's why it's not like a normal isomerase where maybe the alcohol will go from carbon 3 to carbon 2 or something like that. Mutates. This is an epimer. It's an epimerase. And it's called UDP glucose epimerase, which kind of makes sense. UDP glucose is on position. Okay, and then you go back up. This UDP glucose goes back up here to connect with the U transferase, and we make the glucose. The glucose 1-phosphate, they can go ahead and enter into the previous slides that we were showing before. Oh.
Two ductations.
Mm-hmm.
Where is in the second? I understand when you make a ketone, where you're getting the extra proton that's transferred to the NADH.
Yeah.
When you take the ketone and you make it back in alcohol, how do you get an NADH out of it?
Yeah, actually, that's a good question. I'll have to look this one up to see if there's something like a little side reaction. But I got it from your book, and I don't know the mechanism behind this one.
Because you think that you would just take it in.
You think that it's going to be futile in that sense. Mm-hmm. So I will have to look it up, see if there's some type of side reaction that goes on that I don't know about. Okay. Good question. That's a good idea. I'll have to look it up. Or sometimes what we'll also find out later on, and I'm 99.999% sure that this is not happening here, but there are enzymes that utilize, say, for example, an NADH for the first half, and in the second half maybe use FADH2, where because they're huge they literally do look like a little assembly line, and the reducing equivalent on one end is not the reducing equivalent thing on the other end. And this is the way they do normalization and stuff. But I'm 99% sure that this is not one of those.
Because I can see
Right,
it.
because you're doing a reduction here.
Yeah.
So you're doing an oxidation to the sugar here, so therefore this should be reduced. But then if you're doing a reduction to the sugar here, then this should be oxidized.
That's why.
And so I'll go look this one up to see if there's something that's missing here, or to see if they're both a typo.
That's
quite
what should be a
possible.
type of idea. Like you want it to flip around the alcohol. at the
Because the
bottom.
only way that I could think that it wouldn't be is if there's something that if this enzyme here is a ping pong reaction with something else. I don't think that that's true, but there are those kind of, like, for example, I think it's pyruvate dehydrogenase complex. Usually these things were complex after them, to where once again, literally there are multiple components on the big complex, and so what they do at one end is not the final respect to the reduction and oxidation on the other end. Your cytochrome P450 is just something similar with lipoic acid and NADH, I think. I'll look that one up. Yep. Okay. Any other questions? Awesome. Like that would have been more bonus points. Okay. Any other questions?